right, so we're gonna get going. Respect your time here. I got about 6 different big picture problems that I think are gonna be really helpful for you today. Again, this is not on a pre-made sheet. This is just working off of open paper. So I would just make like AP Chemistry, Chapter 8 maybe, Chapter 8 Bonding Review for you. But you definitely will want to write some of this out. So we're going to start right off the bat and going to talk about lattice energies. So you may not want to actually write the 2 numbers, but I do have 2 categories, okay? And what this all comes down to is when I talk about lattice energy, it's called Coulomb's law. And what we have is basically lattice energy equals, remember what goes on top and on bottom? There's 2 factors that talk about when you want to create a lattice, when you want to put 2 ions together, how much energy is released or how much energy is required to break them back apart. What are the factors? Anybody? Charge, perfect, that's one of them. It's technically Q1 and Q2, but you just think of Q and the what? And the R. So basically, it's charge and size, right? That's what dictates this. Please don't overthink this. It's a mathematical relationship, right? The greater the charge, the greater the lattice energy. The smaller the size, the greater the lattice energy, right? So this is what I've done. And I will put these in order on this side. I have randomly picked, these aren't the actual values. If you were just given 4 values, so these are the values. We're going to talk about why. So the lattice energy is 1,000, 4,000, 6,000, and 10,000. Can you pair them up with these 4 salts? So you can work with someone else. You can work on your own. What I'd suggest, the easiest way to do this first is find the largest or the smallest. Don't find the middle right away. So you got to think about what that does. Charge and size. Charge and size. I will tell you this. Charge always wins out. Size changes a very minuscule amount from one to the next. We're talking angstroms. We're talking 10 to the negative 10th meters. So remember, charges multiply. It doesn't matter. A -6 is larger than a -4 up here. They're always going to be negative. You're always going to have a positive and negative charge. Always. They're salts. There's a positive and negative. So think about where they are. What I would do, maybe write these on the side first. Like not right next to each other. Give you a hint. Like you might want to write above this very small, like that's a +2, right? Because that's where strontium would be, and so on and so forth. So what I would do is quickly just jot down all my charges, unless you can do it mentally. You are looking for what on the bookends? Either the one with the greatest charges or the one with the smallest sizes with the smallest charge, right? Again, charge dominates this. So you can't have like a huge charge and be like, yeah, but I found a really small or really large size or small size. Size gets destroyed by the charge in this situation. So I'm going to pause this. We're going to work on this just a little bit. So put all the charges up on top first. That'd be the first step. So again, get the charges. All the charges matter first. After the charges are tied, then the size is taken into account. So I'm going to write mine above here once. Can anybody tell me one that just jumps out to them right away? Like one of the salts and where it goes? What? No? Okay. Can't just say elements and then say nothing. Oh, well, okay. Where does it go? Does anybody have one that just really jumps out, like you really feel confident, like this one has to go here? Again, the larger the number, that means that this would be the larger number, resulting in whatever you did here. Nate, you have one? Why is this the biggest? Yeah, this is dictated by charge. Right, I have the most charge by far. Oops, of course it's going to be separate. Again, charge is always the thing we look at first. The charge has a much greater effect on this than the size. Again, when you talk about the size of the atoms, it's going to change very small increments from one to the next. What's the other one that jumps out at you? Where does the NAF go? The smallest. It's the lowest charges. So now it comes down to this. This shouldn't be a surprise. The ones that are tied are in the middle. So let's just talk about that for a second. Which one, not specifically, let's say smaller size. Which one's that going to be? The -4 or the -6,000? The smaller size atoms. If I have a smaller answer here, what does it make it what does it make? It makes that number larger, doesn't it? Yes. Smaller of my size, the larger the lattice energy. So this right away is going to be the smaller size of the two. So which one is it? Systematically break it down. Ca, I'm just going to write this. This isn't technical chemistry notation, but this is smaller than the SR, right? You got to look cation to cation, anion to anion. You can't go like cation to anion. It doesn't work like that. And then Te to S. They're right on the same column. S is much smaller than Te. So, boom, that one goes here. This one's got to go there. Hopefully you got that right if you tried it beforehand. If you did, that's awesome. Okay. Great question would be, well, what if one's larger and one's smaller? I will make sure that if that's the case, one will be like 2 larger, and then the other one will be 1 smaller. But it won't be like, there won't be equality there where it's like you don't have any idea. Like it has to, it's going to be pretty clear. I'm not getting what I need out of you. This is enough. You should be able to do that already. So how do we do it? Let's just recap quickly. You got to do the bookends first. The greater the charge, the greater the lattice energy. The smaller the charge, the smaller the lattice energy. Depending on if you still have similar charges, it might still, this could have been a 2 plus and a 2 minus, and this could have been a 1 plus and a 1 minus. I mean a 2 plus and a 1 minus, right? So this could have been a 1 times 2, 2 times 2, 2 times 3. Then it would have been all charge. It's not a great test question either. This is a good question because I do charge and I do the size in the middle, so it has a little bit of both. So, okay, there we go. Round 1. Round 2, here we go. Let's make a Born-Haber cycle, huh? Let's do it. So, don't worry about the exact, I'll make this a little bit bigger. So you don't, if you want to write all that down, that's the only regret I have right now is, oh no, spinning wheel. Okay, well, let's just talk as this is thinking. You are going to be given a list of different reactions, basically. Different kinds of a process that could happen to metals and gases and things. These shouldn't jump out at you. This should be very familiar. You have sublimation, you have ionization, you have dissociation. That could also say bond energy, the bond energy of F2. Electron affinity, this one says lattice energy, and then in this case it says enthalpy of formation, and there's a question mark. Now, remind me, what's the other one that can be solved for? I mean, you can solve for all of them, but we're going to solve for what? What's the other one you can? Lattice energy, that's the one we are going to solve for. Oh my God. No. What if I just delete? Okay, let's pause this so people. So you need to understand what you're doing with this. My personal opinion is that you should draw out the generic equation of making the salt. So I'm going to kind of write it over here. I'm going to take lithium. I'm going to add fluorine. And I'm going to make lithium fluoride. Now, personally, I think this helps. Sometimes you're given some extra help. But the states of matter, I think, are important. So lithium would be a solid initially. This is like an enthalpy of formation, right? It's making a mole of the compound from its elements at standard conditions. So this is a gas. And what's the last thing that has to be done right now before I do anything else, like on this equation? That's a T now. Oh.
2 and 1.
1. That's a half. What's the goal? You may not get there, but if you can remember the goal on the bottom, it really does help. So if you know that, that would be really good. And if you can remember that, everything else fills in. So anybody want to just elaborate in general? What's the goal of this? It's a salt, it's an ionic compound. I want gas. More specifically, what gas? Like, they are gases, but there's something else about them. I want ions. I want ions that are in gaseous form, simply put. So I need Li plus, right, F minus. That's it. And in this case, it's a 1-to-1, right? Tomorrow we'll do one more in class. Okay, but this is a 1-to-1. Why? This makes that. The bottom makes the salt. Okay? Now, if you want to, I learned I always made a little gap in the middle, and I made boxes, and I wrote down the lattice energies and all that, but you can just write right on top if you want. But here we go. You know what? Well, here. I'll give you a hint. I'll get you started. There's only so much you're going to fill in. This is a short one. That's actually it. So in between those arrows, you should have letters, maybe states, like symbols and states. And on the arrows, you should have boxes. Or not boxes, but at least numbers. So I'm going to have numbers written right here. You don't have to write the process itself, but got to have a number written. I'm just kind of showing you fill in the blank. This should have something written on each of those, okay? And then we're solving for that. So I'm going to give you a little time, try to construct this by the clues. You're going to be given this, the names of each process and the values. You have to understand where to put them. They can only be used once. I'm not giving you any red herrings, meaning that I'm not giving you something that's not going to be used. You've got to just understand where they're supposed to go. Okay? So my suggestion as well is on the actual test that'll be written out, I would check them off. Like used it, used it, used it. Okay? So work through this. I'm going to pause. Okay. Let's talk about the one no one wants to know. First, what is this? What value? What am I doing to that middle box there? That's the dissociation. So I'm just going to kind of cross that part off. That's 154. Now, you wouldn't necessarily do boxes. It's actually becoming a little cumbersome for me to have that there, but it's more for you. Because, think about this, dissociation. I have F2, and I'm breaking it down into two Fs. What did you start with? A half an F. So you're only going to end up with one F. But you didn't break apart a whole F2, you broke apart a half of an F2. So I have to do a half of that. So here's the rule of thumb, as I just said before. If I'm writing down a value, whatever coefficient is above it has to go into that actual value. So now I don't have a number any longer, so now I'm not going to use a number in the next one. In other cases, just so you know, if this said F2, it'd become 2F, let's say, if you didn't have a half. So I'd have a number here, but then on the next one, I'd actually have a 2 in front of my number, if that makes sense. I think that you can kind of relate those two together, okay? So then there'd be an arrow going down after that. So whatever number is above your values, coefficient-wise, it'll go in front of your energy numbers. Okay? Let's see if you wrote down the rest of them correctly. So here, I have to take Li and do what to it? I have to make it into a gas. So that is sublimation. It's still a gas. So that's sublimation. So that's 161. Now I got to take away an electron. So that's ionization energy. Believe me, these are not necessarily in order. Do not think I give these to you in order. I am not that nice for sure. It's very random. And then there I am. It's just you keep going. Sometimes in certain problems you've seen, let's say it was Mg2 plus, and I was, like, I'm sorry, you're using Mg and that would become 2 plus. And on there it says first and second ionization energies, and then there's only like one number, then you don't have to do it once, and it's just Mg to Mg2 plus. Final one here, I hope that you think that's electron affinity. That's gaining electrons. And then yes, Evelyn, this is lattice energy. You like totes. So how do I get enthalpy of formation? Each column plus my lattice energy. That's how you would do it. So let's do it. So I have 161 plus 520. I have 681 here. I have half of 154 plus negative 328. And then I have to add the lattice energy in there. Negative 617. Anybody else? Sorry. Good. If you are solving for lattice energy, how do you do that? It's your two columns down here. You take your enthalpy, guys, and enthalpy of formation, and you subtract these two, and you're going to equal that. This is always big. If you get a really small number, you did something wrong. This is actually probably the smallest number. Why? Because lithium fluoride is +1, -1, and they're really, well, they are smaller, which does help, but really low charge, really low charge. So the lattice energy is going to be a lot smaller. So that's a Born-Haber cycle. We're going to do one more tomorrow as well, but you're going to have to draw one. You're going to give information like this. You're going to have to draw one out, and you're going to have to go from scratch. So tomorrow, I'm going to be really quiet because if you can't do this and you can't come to this idea, the whole thing is scrapped. Like I'm just gonna say go, because I don't think it's gonna help you. You want to start from scratch. No.
Are they going to be sort of like in order like that? Or like maybe in the
I'm not that nice.
Okay, correct.
But you just wanted me to say that again, or what? Because I said I'm not that nice about it earlier. So, touche. Okay, another problem. Let's do resonance and formal charge. So I have. I have a problem here. NSC minus. I'm going to give you what they look like already. Like these are your possibilities. So here you go. What I want to know, which one's favored? Using formal charges, which one's favored, and show your work. Okay? I'm going to pause it, work on it, come back to it. I'm going to quickly just get started in case. Here, just, if you were doing this at home, let's do one together. So I take the nitrogen, for example. You can definitely have arrows. I would write the formal charge on top. So what we do is we say the number of valence electrons. So this is how many electrons they have in their bond. And then I'm going to compare to what they are doing with their electrons. So they have 2 unshared. And then they have 3 bonds. So 5 minus 5, I have a formal charge of 0, as an example. If you see that bonding happening again, is there an atom here that actually you only have to calculate one time? N, C, or S? C, because it's the same exact bond number and lone pair number. So you don't have to do it once, but you do have to do it. If you're not doing it, you would potentially open yourself up to losing points. So figure out the rest of them, then I'd like you to square or box or circle the correct answer. Kind of just go through these. If you're working on it, just don't look up. Oh, This whole thing is a -1 charge. I'm like, I did this wrong. It's a -1 charge. This thing has to equal -1. I was like, these all look right. The overall formal charges have to reflect the overall charge of the molecule. In this case, I have an NCS -1. So this whole thing has to be -1s, not zeros. We've always been doing neutral molecules. Woo! That's close. So my carbons, I have zeros because I feel good about that. Better question first. What is the least favored molecule? First, second, or third? Third. And the reason why is that you have a -2. You have a 2 that is further away from the bonding or the perfect bonding situation, the least energy state that the bond would be created by having a 2. Okay, so that one for surely isn't it. So then you get to this. And this is really typical for your test that you're going to run into, is that you have a -1, a 0, 0, a -1, 0, 0. They're the same exact numbers, but there's a right answer. Which one is it, first or second? Who's more electronegative? The one closer to the upper right is always more electronegative. Sulfur's more to the upper right. Okay? So this one is the one that has to be favored. Now, I will make sure, see that one scares me only because if I look it up, I wouldn't be surprised. You have your large lecture notes. I wouldn't be surprised if nitrogen and sulfur are really similar, if not the same. Yeah. I will ensure that it's correct. There's a trend and then there's actual numbers. Trends are helpful because we don't have to memorize them. If you had access to numbers, technically nitrogen, I want to go with the trend for today. I'm going with the trend. I'm not making you look up electronegative numbers because, and that's why I hesitated when I asked you guys, is that nitrogen is smaller and there's only one difference. So that's always a little scary. So a better question would be like P or O, because O then is clearly more to the right and it's smaller. I will have a very clear-cut answer. It's the more electronegative. I want to follow trends, not memorizing. So we want the -1 to be on the more electronegative. More to the upper right.
Like, what are you looking at?
Okay, so you want the negative formal charge to be on the most electronegative atom. So you have this situation here, or you have this situation. Okay? So if you both have -1s on 2 different atoms, you want the one that's on the most electronegative atom to be the negative. Okay? Technically, actually, nitrogen's more electronegative though, but I want to go by trends, and that one's closer to the upper right. So I will be. You're not going to get a chart of electronegative values at all. So it's the one in the more to the upper right.
Yeah, so I was just going to say is that, because you're saying for the sake of simplicity, it's the left one, the correct answer is the second one.
For everything that matters to you, it's this one. It's the one I boxed. Because you're not going to get a chart. You're not going to have a chart with electronegative values. So you got to go based on trend. Okay? You are not memorizing that chart. Okay, so if there's a negative, there will be one. I promise it's not going to be 0, 0, 0. If there's a 0, 0, 0, 1, that's your 1. That's what you're picking. Goal 0. There won't be one. Because then that defeats what I'm really asking. I want to get it all done in one problem, and it'll have one with a -1. Might have a positive one in it too. But the -1, we did a good example 2 days ago in your notes as well. All right, let's move on. Okay, little geometry for you. I'm going to do the first one with you. You're going to do the next 2. Okay? So, away we go. this is what I'd suggest. On the side, so don't worry about writing it all. Let's just make a title. You're going to have 3 different columns though. So CLF4 minus, okay? If you are running out of paper, you might want to start over or start in the next spot. Okay, so this is me thinking. Okay, if I had CL bond, I'd have, and you can write as little or as much as you want with TV. I'm not grading TV. TV is a tool, not a way to get points purely from that. How many should I have? Well, this is 7. This is 28, 7 times 4, and then this adds or takes away the negative? Adds. So 8 plus 30, 28? 36? Okay. Write them the same shape twice. We might change the second one. Don't draw these all out. We might change the second one. It's okay. Oh, no. Make that a plus. That's why. No, we can't repeat. I just accidentally hit the negative. So what is that? I wanted a positive in here because that's where people make the most mistakes on. That takes away one. Suggestion. With that, it's hard to do that. Like, what are you supposed to do? Write a -1? Write a, like, what do you do? What I like to do sometimes is actually cross out a number and rewrite a number 1 smaller. See what I'm doing there? Then that takes care of that. I know that does not have. I know that doesn't have 6. I know it has 7. But the positive removes a total electron. So that was my fault. I just wrote that down wrong. I have 34. So what does that mean? And again, you can execute this if you want or not, but it's a difference of 2. The hardest part for a lot of you guys is that you're sitting here thinking, does that mean I add a bond or do I add a lone pair? And if that comes up, you have doubt on the test. I just think about my picture. My picture is too short or too many? Remember, what am I supposed to have? I need to have what, T or V? I need to have V. So is my picture too short or too many? Too short. You got to add dots then. Bonds actually help share more, so you don't need as many. So I need to add 2 more. Why do I do all that? Clouds. I'm just trying to get the clouds. This will not be on the board. Well, we're going to be a large group anyway. This is the goal. You got parent geometry. So 5 clouds. What is that? That's a stick with a triangle in the middle. Right? Immediately, stick with a triangle. The 2 most complicated shapes. One has a stick with a triangle, one has a stick with a square. I have a vertical axis with a perpendicular triangle. I have a vertical axis with a perpendicular square. And that's all that I'm looking at.
Are you going to be a stickler of where we put the pair?
No, but, well, yeah, there are certain spots that are wrong. If you put them on the axis, it's wrong. Because they have to be on the triangle because the triangle is further away from everything else. That's the biggest angle. My suggestion, Noah, is that when you have 1 lone pair, you put it where the 1 bond is. When you have 2 lone pairs, you put it where the 2 bonds are. Because then you can actually you can see the shape. By doing this, I can actually see that. Now maybe you can, but if I do this, that does not jump out the same as a shape as that, to me. And if you had 2 lone pairs, and you did this, that does not jump out the same as if you have 2 lone pairs, drawing it like that. That jumps out more. So I would put 1 lone pair where the 1 bond is, 2 lone pairs where the 2 bonds are. So, parent geometry, what's the name? Trigonal bipyramidal. You need to know these. Molecular geometry. Seesaw. Do you not see it? Do you not seesaw it? No? See? It's seesaw. Hybrid. SP. 3D. Bond angles. 120. Sure. These are the 2 most important ones. I would take those 2 as a full answer. If I ask you to draw it on the shape itself, I expect you to be able to do that. That would be the 90. This would be the 120 if I ask you to do that. Or that would be the 90 on top. You don't have to draw all the 90s. You just have to draw it once. But that would be where they would be all located. If you do a 180, yes, it's from the F to the top F to the bottom F. But if I ask you to draw it on there, you should be able to. And then polarity. All I'm asking is it polar or non-polar? It's not symmetrical, so it is polar. So, what I'd like you to do, I'm going to pause it. If you're at home or here, you're going to work on the next two without any assistance. So, go. And if it has a charge, it should have a bracket with a charge. Yes, very good. So here's some of my work. So those are my T's. It is so vital that you start off slow and you make sure that you have your clouds right, or else it's a hard thing to come back from. So my middle one, the XEF4, I figured out that it's 6 clouds. Right? It's 32, but then it should be 36, so it's a difference of 4, so I'm short by 4 electrons. Okay, so what is that? That is 6, so I make an axis with a perpendicular square. Your lone pairs need to be as far away as possible. Technically, it doesn't matter where you put them. Excuse me. But they got to be opposites. So I would just put them opposites and then put everything else in there. My other drawing, how many clouds do I have? 4. Oh, 4. It's a tetrahedral. Up, over, out, away. I'm going to sign 3, put the lone pair. Let's get rid of that right away so I don't forget. And now I go. So I'm going to fill these in. This is an octahedral. And then I cover up those lone pairs. It's a square planar. Hybrid, 6 clouds. SP3D2. Angles, 90. If you want to write a 180, I'm okay with that, but it's not necessary because it's going, well, yeah, because it's in between each one. If I was going to write it on here, it could be anywhere. I'll write it here. It could be between each of these. And then finally, is this polar or non-polar? Non-polar. It is totally symmetrical. This is one of the only ones that is non-polar, even though it has lone pairs. This is non-polar. Other one, I have tetrahedral. The molecular shape is trigonal, what? Pyramidal, because it rises. Bond angle, 107. Remember, tetrahedral is 109.5. Every time you add a lone pair, it just reduces by 2. So 107, 105. Evelyn? Hybrid, SP3, thank you. Polar or non-polar? Polar. It's not even. It's not even all the way around. You got lone pairs on the top. Lone pair, I should say. So we'll practice this a little bit more tomorrow, but should be able to do these. So I hope that went well. Okay, 2 more pages, and we are done. Okay, bonding orbitals. Bless you. We did this in class today. Yes. So what I want to know is what is involved in each of these bonds. And this is all I'm going to say. I'm going to do one of them. I'm going to do the first one because it's the least involved. So I want to know between the H and the C. So I'm talking about that bond. So I have a 1s and I have a what? Here, let's do this first. Let's do this. In general, fill that in for the whole structure. So fill that structure out first. I know you're probably still writing it. I got all into it. I'm excited. Now, what do you got? What is it? No, just what's the answer? Just say it again. You gave me two answers. That's all. Okay. Okay. I just want to make sure. I'm a stickler for the right answer. So, when I'm doing this one, this is a sigma. Sigma is dealing with hybridized orbitals. So, what is this? What's the carbon? sp2. Because there are 3
Oh, yeah, okay.
clouds. So what I would like to know is what are all the other orbitals involved in all of the bonds underneath these different columns? How many more do you have to fill out total? Like, I know there's but like, how many more of these are you going to do? 3 more? Why? Because there's 4 total bonds. I've done 1 bond. There are 3 more bonds in here somewhere, but they're only under these 2 things. Okay? So, if you can try to mirror what we did in class today, I'm going to pause it, give it a shot. You can write 3 more. Okay. This is the one I hope we agree we're doing 2. You don't have to title them sigma and pi, but it does help sometimes. I'm going to jump back to that one in a second. I want to do the last one first. So make sure you're lining it up underneath the proper elements. So I got carbon first. So carbon still 1, 2, 3. So I have an sp2. And what is the chlorine? Oops, whoa. Was that there before? What do I write? S Y3, 1, 2, 3, 4. 4 clouds, sp3. Okay? Always your sigma bond are hybridized except with an H. So what do I write here? sp2 to what? sp2. Why? 1, 2, 3. Okay? Then the pi. What am I writing? 2p to 3p. Mm-hmm. Oh, that's why I drew those dots on there. That's why they're deleting. So, it's tricky. There are overlapping bonds right here. And these are my sigma. That's kind of confusing, I know that. But then there's these p orbitals that have to float above. Actually, it won't look like that, but this is tough because this isn't actually the shape. But there'll be another p orbital, and this has to rise above. All in said and done, basically what happens is my sigma is hybridized. My pi uses p orbitals. Okay? That really looks sloppy. But that you got to use p orbit. We had those pictures today where like you have a sigma bond. That's my sigma bond, and then you have these high p orbitals that reach over and under, and that's my pi bond. And the pi bond, these are unhybridized because p's are vertical. They're like 90 degrees, 90 degrees. They only sit as 90-degree angles. So they have to use the p orbitals. Why a 2 and a 3? The carbon's from the second row, that's where the electrons would be coming from, and the p is from the third row, that's where the electrons would be coming from, because that's the outer atoms. Evelyn.
So like at the X-rays, these only for pylons, and you asked like this really expensive.
So what I was about to throw out there, what if I threw that there? What if I had given you that hint? What would you have to do to the other one? This would have to be a y. It isn't necessarily a y. It could be an x, y, or a z, but once it's one, it has to be the other because it has to be in the same plane.
So if you don't ask for that on the test,
Then I may
you
not.
have to put it?
Nope.
Okay.
Do you have to put it though if there's two?
You can always put them. You can always just go with it too, though.
Like it doesn't matter if it
Yeah.
does. Okay.
Other questions? I know it's still fresh. This is what you'd have to do. I give you a shape. You might tell me pi and sigma bonds in the beginning, and then I might ask, what are the orbitals involved in these bonds? And you tell me. Okay. Last one. You'll need a sheet, and we'll be done. Bond energy. So I want to do the first one with you. Okay. I think if you don't at least write down a generic Lewis structure on the top or underneath, I think you're setting yourself up for failure. I try to do kind of small ones. So this one, for example, I have HCN. Some of you that have been working on your problems, you already know what this looks like. Carbon bonds 4 times always. So what's missing? Triple bond. Carbons always bond 4 times. So that's what that would look like. That's what this one would look like. And then here, just follow the route. I don't like the right H's if I can help it. Like, unless if it's like the first two where it's kind of hard not to. But like there, those lines have H's. If you feel better about it, great. The second one, before you move on, before you start it, please be aware. You always look at equations and you see if they're balanced. If there's one coefficient, no one ever half balances a reaction. So on a test, it's not like, I only balanced half of it. I got you. If there's a coefficient, it's done. But if there isn't, you need to balance it. And it's a big deal. So you got to make sure you balance those. So I'm going to give you a moment. These aren't meant to be lengthy, but do them. The second one, start to draw it out. We'll come back together and we'll solve it. So you might want you will need your bonding energy sheets. I would do a thorough check when you go through it to make sure that you have not overlooked a bond. All it takes is one, and you're wrong, and you miss it. It's really important to be thorough. Make sure that you have done that. Do you have one, Seth, or else I have another one?
Yeah, I got one.
Okay. I'm going with that. I calculated it twice.
Yeah, I got that.
Okay. If you did not get it right, if you didn't get it right, check this out. Look, do you have the right bonds and do you have the right bond energies associated? Because it's very easy. It's very easy to miss it. It's very easy even to look at the sheet incorrectly. Like, hey, I was looking at the right spot and I just shifted over wrong. Yeah, don't do bond length. Do not do bond length. The bottom. Second one underneath. I'm not going to draw every one of them. I draw the ones that I know that I don't have down. So that's what that one looks like. O2. What's the big deal with that? Double bond. Sometimes it just helps for a visual. Note, I don't care about the shape. Like, I know that that's bent. I don't want to take up all this space. Like, I must make an octahedral. Like, I just need the bond angles. This one's tricky though, because you need the right number of all the bonds with the coefficients. So I'm going to fill them in. If you're not done with it yet, don't look up until you're done. But it's really important the way I'm writing it. I hope it helps. So those are my bonds. Match it up. I see normally a lot of people making mistakes on the right side. You don't do the 6 or the 8. Right? You have 2 OH bonds and there's 4 of them. So now I got to fill in the numbers. I'm going to try to utilize some of them that we already have. So make this. Whoa, wait. Something's not right here. Oh, that's a CC. Oops, sorry. That changes things. See, look at that. I would have made a mistake. Remember, double bonds or multiple bonds are always to the right. What number am I about to write? My double, and if you don't want to look up, but the C double bond O, what number do I have to actually physically write? 799, right? And well, why would it always be 799? Because there's a lot of other things that have a double bond O besides just carbon dioxide. But you got to make sure that you get that right. Bless you. I hope you're doing this all in one foul swoop. You're not like hitting each one, writing them down. Like your calculator can more than handle this. Orders of operations. If you're writing the 2 numbers below like that, you are ensuring that I am able to see. Like if you get the 8530, and I'm hoping that that's right, and not the 6473, I can just go, oh, well, I know they got the right side right. Okay, where's the left side? What's wrong? Like it guides me to it. As we talked about in class, it is not about you hiding what you don't know. It's about showing where the mistakes are so I can actually appropriately give you the points you still deserve. The more negative, the more exothermic. That's the combustion of propane, like in a gas grill. That should make sense that that is an extremely huge release of energy. We'll be reviewing in class tomorrow. Test Thursday. I can't leave.